Hey everyone, welcome back to my daily coding series. This is episode 93. So today I'm going to look at just another advanced graph problem. So I haven't looked at it yet. It's called cheapest flights within K stops. So let's take a look here. I'll try it for about 30-ish or 40 minutes and then I'll look at the solution. So, alright, there are sorry, let me just close out of some stuff. Okay, so there are n airports labeled from 0 to n minus 1, which are connected by some flights. Okay, so these are the nodes. You are given an array flights, flights of I, so weighted edges basically from the flights. There are no duplicate flights and no flights from an airport to itself. Okay, no flights from an airport to itself. You're also given three integers, source, distance, and k, where source is the starting airport, destination is the destination airport, it's not itself, and k is the maximum number of stops you can make, not including source and distance. What do we return? Return the cheapest price. Okay, so so my understanding of this is it's basically like find the shortest path. And when I say shortest, I mean the path with the least weight. But with this constraint, it has to be within. It has to be within k. Within k flights. Okay. So this is very similar to. So the unique part of this problem is the k part. Because if we look at network delay time, which I solved a couple days ago, yeah, with this, it's basically like a implementation of Dijkstra's algorithm, I think, where you just find the number of nodes in the shortest path, right? So return the minimum time. Yeah, so you return the minimum weight. So you have to find the path with the minimum weight and return it. So this one is very similar except k. So the way how I did it before, so usually the way you do this is at every node. So okay, so you just do like, I did a breadth first search, and then at every node you update that node's shortest time if to the current path, like the current time, if it's shorter than the shortest time. So basically at every node you just keep track of like the shortest time it takes to get there, and then at the end you just return the shortest time for the end node. So in this case, it's a bit different. So let's say we reach a node and we have like 2 flights remaining, and so far it's taken us 500 time. And let's say we have another path which we have 2 Ks remaining and it takes us 600. So at that node, we would not have to store this information. Like this would be a dead path because it would just make more sense to take the other path with 500. Now, if this was, we had 3 flights remaining and it was 600, now we would have to store both of these because even though this has, and we want to minimize, yeah, I'm assuming that, yeah, so this is the price. Okay, so we have 3 flights remaining at this path, but so we want to minimize the price. Okay, so actually in this case we could discard this one as well because price only goes up. And let me go back to the other example. So in this case, we have 2 flights remaining, so we want like a higher K, but we want a lower price. So yeah, in this case, this price is just higher. If we change it to 3, we have more flights remaining, but we already have a higher price. So Yeah, so this is interesting, actually. I don't know if we have to keep this or not. Because on one hand, we have a higher price, but on the other hand, we have more flights to work with. So it's possible that this um, like route would not be able to reach the finish line, and this one would just because it has more flights. So we would have to keep both of these. If we had something, so let's say we had K is 2 and 400. So obviously with the same K, so I'm just gonna write this down. So with the same K, so I'll just say only include lower price. I don't know if I should just store the lowest price for every K and then do that. Is it ever possible? So what if I have less? So if I have less and I have a more expensive price. So in this case, we would never want this path because we have less flights to work with and we've spent more money. So, okay. Only include lower K if price is also lower. And then I think we always want to include higher K values. Yeah, so what this would mean though is for every node, we'd have to go through like all of these. So we wouldn't include this and we wouldn't include this, but we would store up to like K could be up to destination, which could be less than n. So we could store up to like 100 of these, and there could be 100 nodes. Pretty small numbers, so I think that would be fine. And maybe that's the intended way to do it. Alternatively, what we could do is just solve the problem, like do Dijkstra's algorithm K times. So do Dijkstra's algorithm with, but only allow us to go 1 from the start, and then do it again, but only allow us to go 2 from the start, and so on. And then and then the first time, the first K value that has a solution, it would be that solution. So like, and that is because well, maybe not, because maybe, yeah. So we would do it all the way up to K and then just restore, or we would return the value. So we could do Dijkstra's algorithm K times, or we could just do it one time and then keep track of at every node all the different paths, all the different possible optimal paths, which I'm thinking I like this one better. So we're basically going to do the same thing, but instead of storing a number, we're also going to store a K value. And because that leads to more possible shortest paths, we have to store all of the possible shortest paths, but we can trim them based on this. So like if they have the same K, so we'll probably have something like a dictionary. So maybe like each graph would have a dictionary, and it would say, okay, so for K equals 2, the minimum that we found is 400. And then let's say another path comes in that says, okay, I have 2 flights remaining, but I've only spent 300. Then we would just update it like this. Yeah. And then if we added something that's like 1, we could just do like 1 700. Obviously we don't need this, but I'm just thinking if it's worth it to not, because how would you check this? You would just say like, okay, so let's imagine for a second that, okay, so we have 2 300 and then we added 3 800. So this still could be a possible answer, but then we have 1 700. So this is bad only because 2 300 is above it. If these were flipped, so yeah. it might be hard to check for all of that just because the dictionary is always changing. Because if we start with 2 800 and then we find a 3 300, then that means we can actually delete everything below it that's less than 300. So it could be like every time we add something, we can check to delete things. But at that point, I'm wondering if it's just more cost intensive to do that than to just keep the original. Or maybe instead of deleting it, what we can do is when we iterate through it, we can start from the top and then say, okay, so we have 300 as our minimum. And then if anything after that is less than 300, we just ignore it. Okay, I like that. So we'll keep all values in the dictionary, in the nodes dictionary. Keep all k key value pairs in the nodes dictionary. Iterate when using them. Iterate from the highest k value and don't explore any paths with lower k values and higher ticket, higher prices. Just logically speaking, like, it's always better to pick this one. There is never a case where this has a shortest path that this one doesn't have in less time or with less price. So we'll do that. And then, yeah, obviously only include k if it's lower. And with this one, this is the obvious one. And then with this one, only include lower k if price is also lower. So let's assume that a path is 1 and 1600. How would I think this is what I'm saying. So we don't have to do this because it will get cut off by this. Yes, exactly. Yeah. And if we had 800 and 300, we would say, okay, the minimum so far is 800. So we'll explore it. And then, which is what we want because this could be it. And then 300 is less than 800. So we'll update our minimum and then explore this one because this could also be it. But if we have anything with 1 that is greater than 300, then we don't want to explore it. So that looks good. Okay. All right, so the first step, so we're given a 2D array. So probably we want to build the graph first. And it's a one-way graph. So I would say build the graph. And we'll have it be an adjacency list. So for instance, node 1 connects to, then we'll have a list of tuples, which will be, we'll say like connects to node 0 with 100, and then node 2 with 200, etc. So it'll be the destination and then the price. All right. We also need to keep track of the node. I'll just say the node information, which is basically like the minimums that we found so far. And how I'm going to do that is we could have it just be a list of tuples, I guess. These could be tuples. Yeah, so we'll have a well, maybe it could be a list. Well, we want to start with the highest Ks. So so the obvious way to do it would be every node, and our nodes are numbered from, so we don't really need a dictionary. We could have it be a list and use the index, but just to keep it simple, and also too, this would work better if it wasn't just numbered from 0 to n-1. So I'm going to keep it with the dictionary. So an obvious way to do it would be we would have the key be the node, and then inside would be a list of tuples, and the tuples would be this information. So we'd have like, okay, so for node 1, it has a path. These are all the possible paths. So this information would tell us that one path has all right. So this information would tell us that one path has 2 flights remaining at this point, and we've spent $400 so far. And another point is 3 flights remaining and has $600. But I'm thinking, right, we want to... So we could always have this... We want to iterate from the back. But there's no guarantee that these will be sorted. So what we could do is have it be like just an array. So we'd have an array of an array. Or could it just be one array? I think it could just be one array. And then we'd have like, maybe we'd initialize them all to -1. So these are all the k values. So it's like k is 0, k is 1, k is 2, k is 3. So then at k equals 2, we'd set it to 400. And k equals 3, we'd set it to 600. And then that way we can just like iterate from the back. The reason I'm doing it this way is this will always put it in the right place. Whereas if we do a list of tuples, well, maybe then, since this will have a lot of empty space, could we possibly do it as... We could also, so that's another option, so I'll leave it like that. We could also do just a dictionary that points to another dictionary. So inside this parenthesis will be a dictionary, and then we could just have 2 400, 3 600. Yeah, I'm just thinking on how I'd iterate backwards through this, because is it possible to have 3 and 2 without having 1? Yes, definitely. We can't really use like the length. We could sort it. I don't know, maybe this is actually the best, and then every time we'll just skip the -1s. Because what you could do here is just say for I in range, and then just like iterate through it backwards. And then it would start at here, and then it would go to 3, and then it would go to 2, and then that's just like your k value. Whereas this, yeah, let me try to articulate what I'm thinking. So you can't just take the length of this and go backwards, because there's no way to tell if this is 2 and 1, or if this is 3 and 2, or if it's 5 and 4. Like, there's no way to tell. And it's also not sorted, so so with the dictionary, you would need to know the exact values to look it up. With this approach, you don't have to do that. You can just start from the back and then go to the left, but it's not sorted unless we want to add extra time. So I would say, in this case, it could be 3 and 2. So if you just go in reverse, then you could get 2 and then 3, which is not, it doesn't maintain this requirement that we have. So I think I'm going to use this way because that way we always know it's going to be sorted based on the index that it's at. And we can just do that in O of 1. It doesn't require extra sorting time. Yeah, it's always going to be sorted, and we know exactly which value is which. Okay, so the node information, every node will have an array of, in this case, it would be of size. So k has to be less than n. So it will be of size n minus 1. So I'm just going to write that down. So every node will have an array of size n minus 1, which basically will store the minimum, which stores minimum of, I'll just say minimum price at every k value. We will iterate through it backwards, skipping negative ones. All right. Okay, so we'll have these, and then we'll basically do like a breadth first search. All right, so now that I have the data lined up, I can write some pseudocode for it. So what we're going to do is, well, we're definitely going to have a queue, and I don't think we're going to have a visited set. I don't think that's necessary because we are going to visit things multiple times. But of course we don't want an infinite loop. So what's going to happen is this node information will provide us with the information we need to decide whether or not to add a node back into the queue. Okay, so we'll initialize the queue, and then, yeah, we're going to pop from all of these. So what we're going to do is the queue is going to have in it the start or source node, they call it, right? So we'll have the source node in there. So we'll have the queue will have the source node, and then the node information to have, it will be like source node, and then in it will be one tuple. There's only one path to get to the source node so far, which will be k. We have k tries left, and our price is 0. So that's this. And yeah, so it would actually look like this, I think. So if we have right, so this means how much price if we have 0. So we do all the way to k. But so let's say k is 5. It would be 0, 1, 2, 3, 4, 5. Maybe we make this of size n. So first of all, my first question is it possible that we would ever store, we have 0 left? I think we would store that. If we have 0 left, then that means it's, yeah, we do want 0 left. So if we have k left, then this should be, then we would want to index k. So I think it would be of size n, because it's really like k plus 1 minus 1, because it's size n minus 1, but then we have to add 1 because we want to index it at k. So we'd have it like this. This is how we'd initialize it. And then, yeah, it's of size n. So for instance, if there's 6 nodes, that means the largest k value could be 5. It has to be less than. So therefore 0, 1, 2, 3, 4, 5. Yep, so the length has to be n. All right, so we'll initialize that. And then what we'll do is for this node, So I guess we could say, so iterate backwards through. Okay, so we'd pop from, so we'd say while the queue is not empty, we'll pop from the queue, and then we'll say for I in range length of info of source, which is this, -1, and then iterate through it backwards. So I'm pretty sure this is, so the length -1 would be 5, so 0, 1, 2, 3, 4, 5, and then we'd keep going. Okay, yeah, so I is going to be every k value, so maybe we can call it k, I'm not sure. So what we're going to do here is, first of all, if let's just get like we'll say mins equals info of source, so we don't have to keep writing that. So this array I'm calling mins. So if mins of I equals -1, then we get out. If it doesn't equal -1, then what we want to do is explore all of its neighbors with this information. Okay, so if it doesn't equal -1, so what we want to say is for neighbor in graph of source. So for all of the neighbors in, and then instead of source, we'll just have like node probably. So for every neighbor in, yeah, so for all the neighbors, and this is just like the source, it's, Python is pretty much pseudocode, but all right, so for every neighbor, so in this case, we would have found 0. So I is k. All right, yes. So mins of I is the price. So let me just, for variable namesake, I'm going to change it to k. So we have all these k values. When the value itself is the price with k attempts left. So with so it has with 5 attempts left, that's k. The price so far is 0. So that's information that we need. So for every neighbor, we want to add them to information if it's not in there already. So add neighbor to info dictionary, and then so set info of a neighbor. So this is their mins at index k -1 to be we'll say price plus weight of edge. So what this means is, so we're gonna, so for instance, if this node connected to another node and there was a weight of 500, we would say, okay, so we have k -1 flights left. So this would be an info of the neighbor. So at index k -1, we would, also we need to make sure that there's no index error here, but at index k -1, we would set it to whatever our current price was, which in this case was 0, plus the weight of the edge, which is the price of the flight. And also what we have to do is yeah, so if we have 0 flights remaining, and we also have to say that it's the maximum number of stops you can make. So we'd stop here, and then if we go, yeah, so that's another thing that's a little confusing. So in example 1, we have k equals 1, and that lets us go from, and then, so source is 0, destination is 3. Okay, so it doesn't include the destination. I wish it wasn't worded like that. So the way that this is set up is that it assumes that every edge that you take is -1 to k. Unless it's the destination. So could we just give it like... I'm wondering if hopefully I could just like add 1 and it would work. So k is 1. But yet they take 2 edges. So we might just be able to add 1. But I'm wondering if that will mess things up because it only applies to destination. Like, I wonder if because I'm giving them an extra flight, if that will mess up the information of all of the non-destination nodes, but maybe it won't because for the path... Yeah, so in this example... Alright, let's look at this example. I guess I could finish the pseudocode and then I'll look at the example. So right now my plan is to finish the pseudocode as if the destination was counted as a flight, and then I'll revisit it after I'm done with that. So we'll set the info neighbor at index k minus 1 to be the price of that. And then we also want to... So I'm also thinking that maybe in our... in our queue, instead of just having a queue of nodes, we could maybe have a queue of tuples, which would be the node and the k value. Because here when we're adding it, so we would basically add... how this algorithm would work is we would say add neighbor to queue. And then what it would do is go through all of its neighbors again. But that doesn't seem good. So maybe what we could do is have... So if we change it to just be like... Alright. So I'm going to keep that, but then I'm going to add... So I'm going to try to... So inside the queue we'll have source and then the flights left. And then we'll say node and... I'll just call it flights for like remaining flights. And is it possible I just... Because this information is still useful, I think, for every node to have. But instead of iterating through them, maybe we can just say... Um, maybe K is actually just given as flights. So now it will just check. So price will be equal to mins of K. So we popped from the queue, and now this is like, okay, we're at this node, and we have 3 flights left. So the minimum price we have so far with 3 flights left is this, is price. So I think this is where we could check. So what is price? It's kind of like min price so far, right? So we have this. And then we'll say okay, so we'll do info of node of K. What is info node of K? That is the minimum so far. So I guess we could set all of these to infinity instead. Or is it when we add it, we check first? I think maybe we check first down here. All right, so I'm thinking of order. So something that can help with order is like the first thing that you want to do. So with source and K, and if we initialize it like this, which means the minimum we found so far, maybe it's all infinity. But we have to get like the price of 0 from somewhere. In this, do we just also pass that? I mean, maybe that makes sense. And then, so we pop it, and then we check if info of node, which is now this, at index K, is greater than 0, or we could say if it's less than or equal to 0, then we'll just get out. Or not 0, but price. So if this is what we found before, so if it's less than the price now, then we can just get out because we've already found a shorter path. So okay, otherwise this means it's the shortest path. So in this case, we want to set info node of K to be price. So this is the new minimum price. And then for every neighbor, so we'll add it to, or should this already exist for everything? Because it's already predetermined that it's going to be, and source is always 0, right? Or is source not 0? No, source is not always 0. I'll just do it this way where we add as we go. And then, All right, so this is where we set it. So I think what we want to do here is well, this is the part where we yeah, maybe this is fine. So we just add so what are we going to add to the queue? We want to add neighbor. No. What do we want to add? We want to add the next thing to be explored. So it would be like neighbor k minus 1 and now the new price. Yeah, so it'd be price plus weight of edge. Like this, right? And we're only adding to the neighbors if this is the shortest thing that we found so far at that k value. So whenever we pop something, this could be the shortest that we found or not. If it's not the shortest that we found at this k value, then we'll just forget it. And then this will eventually empty the queue when we found all the shortest paths. If it is the shortest path so far, then we'll update our like memoization, our info, to be price, which is basically the minimum. So info is like the mins. And then, so instead of info, I should probably just call it mins. So this part, I wonder, like, we don't really use mins until here. So, I don't know. Maybe mins dict should be initialized already. Yeah, so we could just have it like all nodes. And then the only thing that would change is, so we'd always have k remaining flights and a price of 0 from the source node. Yeah, so we'll pop from that, and then okay, yeah, I think this makes sense. So if we walk through an example, and then so I expect k to be off by 1, just because of the destination not counting. But if we walk through an example, all right, so I'm gonna delete this, and then I'm not doing this anymore. And I think I have a good idea of we're not iterating through it backwards anymore. We're just kind of using it as like a lookup table. It's sort of like a 2D array, honestly. Should I just make it a 2D array? I think it might be smart to make it a 2D array. I think I'm gonna make it a 2D array. So we'll have like the first array, check the first array. So the index of the subarray will be the node, and then in here will just be like infinites. Okay, so in this case we have 4 nodes. So, and what's k? K is 1. What's n? Well, I guess we should set it to k plus 1. Just be size k plus 1. So in this case, it would look like this. All right. So now we'd add. We'd add source, which is in this case 0. We'd add 1, and we'd add 0. Okay, and then we'd pop it. So node, k, and price are these. So we do our lookup table. If the minimum infinity, so yeah, at node, so at node 0 at k, so k is 1. So right here, if infinity is less than price, which is 0, so infinity is not less than price, so we'll ignore this. We'll set this position to be 0. And then for every neighbor in the graph, so we popped that. For every neighbor in the graph, we will add the neighbor with k minus 1 with price plus the weight of the edge, so 200. All right, and now we'll pop it again. So node is 1, k is 0, so right here we'll make it 200. And then add the other, add its neighbors, and this has been popped. Okay, so we'll have 2 with k negative 1, which doesn't really make sense, and then 300, and then we'll also have 3 negative 1 500. Okay, so I'm wondering if it should just start with k plus 1 and just say like and at this point we could say so after we update this part, only add more if k is still positive. And then at the end we would just return the minimum destination. Yeah, that's fine. We could also just return the first non-infinite value, but alright, I'll try putting this down. I don't know if the negative 1 will like mess up stuff. Like we're setting it to k plus 1, so I don't know if that will mess up stuff with the non-destination ones. Hopefully it doesn't. I'm going to assume that it won't, because we're only interested in how it affects the destination anyway. So all right, so first of all, the minimums, I need it to be an infinity of size k. plus 1, right? So this will give me a list of infinities times k plus 1. And then this has to be copied. So this is a list. Alright, let's not do list comprehension. We'll say mins equals empty list, and then for blank in range n, or I guess, yeah, n. So in this case we had n was 4, so yeah, we want 4 of them, and we'll just say mins dot append a copy I think I need another parenthesis over here. So this gets evaluated to a list, and then I'm just copying it. I think we don't need the copy if we do it this way. Hopefully. Alright, so, and I'll just double check that too, but okay. So let's see here. Can only concatenate list, not integer to list. Is this being... Oh, this... So this is being evaluated as integer. So I'm multiplying the list by a value. I thought you could do that. So if I have times 5, I thought this would give me 5/8. Let's see. It does. Okay. Yep, it's the exact same. Is it because this is not a constant value? Let me try that. But k plus 1 doesn't work. K is a value, right? Maybe parentheses will fix that. Yeah, okay. And now let me just make sure. So if I change mins of 0, 0 to be 5, I want to make sure it only affects one of the lists. Alright, it does. Okay. Alright, so mins is set up like we need it to be. Alright, and let's say from collections import q. And then q append left, we want the tuple with the source node, which is an integer, k plus 1 and 0. So we'll pop from the queue. Then filter out anything that has a shorter price with the same k. If it is shorter, then we will update it. Alright, so after we update it, we only want to add more if k is greater than 0. So we'll get rid of this. we'll get rid of any that k is negative. But, well, yeah, we still want to include the negatives. Or do we not? We're starting with k plus 1, so I don't think... Let's just say or k is less than 0. Alright. And then for neighbor and graph node, we still need to build a graph, of course. We'll say q. Well, maybe we could say q dot append left. We'll add the neighbor with k minus 1 and price plus, yeah, this is graph of node is actually a list of tuples. Price plus cost. I'll just call it weight to make it more transparent. All right. And then at the end, hypothetically, we would want to return the mins of destination, just the minimum value of that. Yep, and we have to build a graph. So, yeah, so for edge in flights, let's just say source destination k. I don't want to redo k though. Just say start, stop, and from I to I price. So if start is not in graph, then we'll say graph of start equals empty list. If stop not in graph, graph of stop equals empty list. We might not have to do this. It's not a two-way connection. So then we'll say graph of start dot append the tuple. How do we want it to be? The neighbor and the weight. Like that. Alright. Let me see if this looks like how we want it to be. So yeah, it's actually dec when we do it this way. Q dot append left. What? Q equals collections dot dec of this tuple. All right, let's see what graph looks like. Zero is connected to 1 with a flight 200. 1 is connected to 2 and 3 with 100 and 300, and 2 is connected to 3 with 100. Okay, good. Yeah, I'm really used to building the graphs, which is good. Okay, mins is good, graph is good, so now it just comes down to this part. I don't think this will work right away. Q dot pop needs an argument. Is it pop right? It shouldn't be pop right. Why does it need an argument? Okay, I think usually what I do is pop left and append right. No, just append. Yeah, I think I do pop left. I don't know what normal pop is on a deck. Pop left. Needs an argument? What? Unbound method? Oh. I think I need those parentheses there. Okay, good. So I don't need this one. There. Okay, that's better. All right, so we have a list index out of range. Yeah, so let's just switch that up. Well, that's not going to fix anything. So it's probably node. Let me print node in K. Node is 0 and K is 2. So yeah, K is out of range. I think... It might be K plus 1 and then plus 1 again. Okay. So it's saying that that's not a key in the graph. That makes sense. Yeah. So if it's not in the graph, I could say graph.get node. So what get does is it's the same thing, but you can also provide a default value if it's not in there, which I'll say is an empty list. Okay, it actually worked for the first two. My return type was infinity. Is there something I'm supposed to return if it's a okay, if it's not possible? Okay, so we'll say result equals this. And if result equals infinity, then return -1, return result. Wow, alright. Great, I got it. It was an hour. I don't know if that problem was deserved an hour. What was hard about that one? I think the realization for me was, I think that the way I was storing the data, that I should have just stored it as a tuple, was what I realized, instead of having that array, because we only want to add the neighbors at a specific k value. Yeah, so this one really wasn't that hard, I don't think. Maybe it was, I don't know. I feel like I've done problems like this, so I'm not sure why it took me an hour. Maybe, I don't know, it felt challenging. It felt challenging for sure. Yeah, let's see the time complexity is m times k. M is the number of flights and k is the number of stops. So this says linear space, so I don't use linear space. And M is the number of flights. Yeah, this reminds me, so what are some things I have to do? Look up BFS and DFS time complexity. I feel like that would be good to just know. And also there was something that I didn't look up last time in the network problem. I had like a similar issue twice and I didn't look up. There's something I wanted to look up. Yeah, I don't remember. Next time I encounter it, I'll look it up, but okay. Yeah, so I guess it was just simple as it was as simple as just adding k plus 1 because the destination didn't count. So I'm glad I kind of just went with that and trusted my intuition on that and didn't like overthink it too hard. Uh, yeah, I feel pretty good about this one. Like I said, it was just how to use the data or like how to structure the data was what it came down to. So I want a queue of tuples, and for the info or for the mins, I just need to store like one value basically. Okay, yeah, so that's it for today's episode. Thank you guys for watching, and I'm gonna record another episode after this because I didn't record one yesterday, so this one will go up for today. I'm still on schedule, but yeah, just got to do 2 today. All right, well, thank you guys for watching.